Now, electrons are so important to us because, in fact, from a practical perspective, we've been able to harness what they do for us. And as you look around a room, everything you see in the room that is driven by electricity coming out of a wall socket, that ability to turn on the lights, or this video camera that's taping me, is a result of the fact that somehow we've been able to channel these electrons and make them move in controlled ways so that they can generate a certain current across a certain potential difference so that we can do work. So that's one of the reasons we're interested in electrons. We're also interested in electrons because almost any portable device you have, like this particular device I have right here, is driven in the same way by electrons, not coming out of a wall, but coming out of a battery. This ability to control the delivery of electrons that achieve a certain current across a certain potential difference to be able to do work, that also is something that we take enormous advantage of. Now, if we take a look at the electron in the context of how it compares to other small particles, you see why it is such a neat thing for us to work with. I want to compare a proton, which I show you right here, to an electron as a fundamental particle. This fundamental particle called a proton here, it has a certain mass and it has a certain amount of charge. And we're going to be talking about charge in just a moment, but I want you to look at it, and I want you to compare it to an electron and its mass and its charge. Notice that the charge per particle for an electron and for a proton are the same, 1.6 times 10 to the minus 19 coulombs. Notice, though, that the mass is very different. There's about a 2,000-fold difference in terms of the mass of an electron compared to a proton. In other words, if I wanted to look at the charge per mass of an electron versus a proton, there's 2,000 times as much oomph. If you wanted to look at it simply in that context, you can see why we prefer to harness our electrons. Never mind how much more easily one can do that. The fact of the matter is that you get 2,000 times the oomph for the size. And that's what makes this such a profoundly important fundamental particle for us to work with. I put down, for comparison purposes as well, a neutral hydrogen atom and a sodium ion. You'll notice that it's important that I have the charge, because then I can take advantage of establishing electric fields so that I can prompt these particles to be able to move and do work for me. That hydrogen neutral right there, because it has no charge, isn't something that I can move across potential differences. So I've got to have the charge. I also put up the sodium right there, which is 23 times larger than even a proton, so that you can see that, yes, once again, on a per charge basis, everything's exactly the same in terms of the amount of charge per particle, but because it weighs, in this particular case, not just 2,000 times as much as a proton, it's 23 times 2,000, so this thing's about 50,000 times larger than an electron. So on a per mass sort of basis, you get 50,000 times less of the oomph that you do here. Not that protons aren't enormously important in terms of doing work for us across in acid-base reactions. Not that sodium ions aren't important for us. For heck, I mean, it's how we drive much of the work that gets done in biological systems. But this is the thing that we're going to be taking a look at in the understanding of electrochemistry as the way we drive most of the very practical types of work that get done in not just chemical systems, but how those chemical systems are realized in the real world for us, in batteries, for example, or in what comes out of a wall socket.